Hi, Alexi from Opto 22 here. Welcome to part 2 of our series showing how to use Opto 22's Intelligent Remote I/O with Allen Bradley Logic Systems. For all the videos in this series, we're using an Allen Bradley 1769 L32E Compact Logix controller, Opto 22 Snap I/O, and a load panel. The first video showed how easy it is to establish communications between a Snap I/O and RS Logix controller. In this screencast, I'd like to take the next step and demonstrate the distributed intelligent features of discrete Snap I/O. Because remember, Snap I/O is much more than just an Ethernet IP bus coupler. On the digital side, Snap I/O handles all the features you see here, such as high-speed counting, pulse generation and measurement, and time proportional outputs. These features are configured and calculated down at the I/O unit level, freeing up the main controller for other tasks. In this screencast, I'll demonstrate 3 of these features. First, we'll configure a standard digital input as a counter and show how easy it is to read and clear the counter from RS Logix. Next, we'll configure a watchdog for the Snap I/O unit and sound an alarm when the watchdog is triggered. Finally, we'll configure a digital output with a pulse train and trigger the pulse train from RS Logix. Let's get started. We'll be using the Ethernet IP configurator, a free utility. We'll start with our discrete input point that we'll configure to be a counter. The digital input module itself was configured in part 1. The input I want for the counter is wired to the first channel on the module, so I'll select that channel and click Add. I'll give the point the descriptive name of, let's say, bottle counter. Let's take a look at the features available for this digital input. Snap I/O can automatically keep track of how many times a digital point changes from off to on. It can also measure the duration of an on or off pulse, as well as the period or frequency of a digital signal. Snap I/O can also keep track of how long a point is on or off. On and off input latches aren't listed here because digital inputs automatically have that feature and they don't have to be configured. I'll select Counter and click OK. And we've completely configured the first point on our module. You may notice that this module has 4 points or channels. Each of these 4 points can be configured independently for different functions, so we're not limited to having the other 3 points serve as counters. Now, in order to get the I/O data into RS Logix, we need to specify it in the implicit message packet. To do this, I'll click on the Configure Assemblies tab. We already have 2 assembly instances started from our last example. Remember that input instance 100 is the input instance from the I/O to RS Logix, and instance 101 is the output instance from RS Logix. We want to read the counter value into RS Logix, so I'll select Assembly Instance 100, the inputs. I'll click on Add to add an assembly member. The Ethernet IP configurator lets me put in a description, so I'll type bottle counter. I'll choose the class discrete input points, and I'll select the bottle counter as the point name. Let's take a closer look at the choices under attribute. Value would show the state of the input. The ones prefaced with feature relate to the feature we configured for the point. In our case, it's a counter, so the feature value would return the value of the counts for that point. Notice we also have access to the on-latch and off-latch status for this point automatically. I'll select feature value and click OK. I don't want to fill in the rest of the I/O module. I'll click OK again. The feature value takes 32 bits because it's a 32-bit counter. So unlike the status of a discrete point, which is 1 bit, we don't need to add any padding to get the required 32-bit word. And that takes care of our inputs. But if we want to be able to clear the counter value from RS Logix, we need to be able to write to the Snap I/O. So we'll add an assembly member to our output instance. I'll select Assembly Instance 101, which is our output instance, and you can see we have a digital output from the previous screencast. I'll click Add. It never hurts to add a description, so let's type Clear Bottle Counter. The counter that we want to clear is on an input point, So that's why we want discrete input selected here. I'll choose my point. And now I'll choose the attribute clear feature value and click OK. I'll click OK again. The clear counter instance only requires 1 bit. So first let's move the padding down to the bottom, and then we'll modify it. Because we have 2 bits, we only need a padding of 30 to get the required 32-bit word. Click OK. To make sure everything is OK, I'll click on Verify. Looks like there's no errors here. Notice I have 3 32-bit words in my assembly instance 100 and still just 1 32-bit word for the assembly instance 101. Remember those numbers because you'll see them again. Now let's click Download to download the configuration to the flash memory of the SnapIO unit. I'll click Close, and for good measure, I'll click Save so I don't lose my work. Now we'll turn our attention to RSLogix. Our SnapIO is configured as a generic Ethernet module. The name and IP address of our I/O haven't changed, so let's look at the connection parameters. Because we now have 3 32-bit words coming from our SnapIO, I'll change the assembly instance size here to 3. The output assembly instance 101 is still just 1 32-bit word. We're not even using the configuration instance, so we'll leave that alone and click OK. Now let's look at the controller tags. The counter is on our input instance, so I'll expand this a bit. The counter is on the 3rd 32-bit word here, so I'll type bottle counter in the description. The clear counter field is on the output instance, so I'll expand that. For this we're using the 2nd bit, so I'll type clear counter in that description. Alright, we're ready to test it out. I'll go to Communications, Download, to download the project to an Allen Bradley Compact Logix controller. I'll click Download, and yes to run it. Keep your eye on the field for the bottle counter. If I flip the switch on my load panel a few times, you can see the value increases. Remember, this counting is done by the I/O unit. The controller is simply reading in the value from the I/O. Now let's clear the counter. I'll go to the clear counter field and enter a 1 to latch the counter value, and a 0 to clear it. Notice that the value of our bottle counter is now 0. Pretty cool, we've written to the SnapIO. Now let's demonstrate the watchdog. The watchdog in SnapIO monitors the health of the comms between the PLC main rack and the remote I/O. The watchdog timer can also execute the fail state of a discrete point or the fail value for analog points. For example, if there's no communication from the main controller, the SnapIO can turn off all the pumps to avoid overflow. To see how this works, we'll leave RSLogix running because we aren't going to do any programming in RSLogix. Instead, we'll go back to the Ethernet IP configurator. Our objective is to have an alarm sound if there's no communication between the controller and the SnapIO for 5 seconds. So the first thing we need to do is configure the watchdog timeout period for the I/O unit. I'll double-click Snap Intelligent Remote I/O over here in the tree. I'll click Yes for the watchdog, and enter 5 for a 5-second watchdog timeout period. And I'll click OK. Next, we need to configure the alarm point. So I'll go to Configure I/O Modules and Points. I have an alarm wired to the first position on a digital output module here. So I'll select point 0 and double-click on it. I'll type alarm as the name. I'll click Yes for a watchdog, and enter on as the fail state, and click OK. I don't need to configure any assembly members. All the action takes place on the I/O unit, so I just need to send the configuration down. I'll select Tools, Download Configuration to Opto 22 device, and click Download. Let's return to RSLogix, which we left running. Everything is fine. If I flip the bottle counter switch, the count increases. Now I'll cause a problem, and it won't be for the first time. In this case, it'll be by disconnecting the Ethernet cable attached to the SnapIO. We'll wait for 5 seconds, and then the alarm sounds. Let me just shut off the audio here. But notice no programming in RS Logix, just a simple configuration for the I/O. This feature can easily be programmed in the field for the I/O without having to touch the main controller software or hardware. And because SnapIO is intelligent, it'll keep on doing its job. For example, it still keeps track of the counts on our switch. To show you, I'll flip the switch a few times. RS Logix can't update because the I/O isn't connected, of course. Once communications are reestablished, the value of the bottle counter automatically displays the correct value as kept by the SnapIO. We're done with RS Logix for the moment, so let's take it offline. I'd like to demonstrate one more cool discrete feature, so let's go back to the Ethernet IP configurator one more time. We need to configure another digital output. I have a LightStack LED connected to port 1. I'll type the name LightStack. And now let's look under Features. You'll see we can configure the point to be a time proportional output, or TPO, or a pulse train. Let's select pulse train. I'll enter a period of 2 seconds. I'll keep the percent 50%. I'll put an initial delay of 1 second. And let's have 10 pulses. I won't set a default watchdog state for this point, although I certainly could. Let's click OK. We want to be able to trigger the pulse train from RS Logix, so if you guessed we'd be adding an assembly member, you'd be right. I'll click on the Configure Assemblies tab and go to 101, the output instance. We'll click Add, and I'll enter Start Pulse Train on LightStack as the description. As the class, I'll select Pulse and TPO Generator. I'll select the LightStack point name. Once I do that, Ethernet IP Configurator confirms that a pulse train is configured on this point. If I selected a different point without that feature, such as Alarm, the message doesn't appear. So I'll go back and select LightStack, and under Attribute, I'll choose Start. I'm going to move the item up in the list, and now we need to change the padding. We have 3 bits we're using, so we'll need a pad of 29 so that we have a 32-bit word. Great! Let's check our work by going to Verify. All looks well, and we notice we still have just 3 32-bit words on the input instance and 1 32-bit word on the output instance. That means we won't need to change the configuration of our generic Ethernet module. Now let's click Download to download the configuration to the flash memory of the SnapIO unit. I'll click Close. Going back to RS Logix, let's update the description for the field used to start the pulse train. We'll need the output instance tags, and it's the 3rd bit. I'll type the description, Start Pulse Train. Now let's download the project. I'll go to Communications, Download, click Download, and yes. Okay, now I'll enter a 1 for the value in the Start Pulse Train field. Check out the load panel. SnapIO is generating the desired pulse train on the LightStack output. Sweet. Thanks for watching part 2 in a 4-part series of videos. We showed you how to configure distributed, intelligent, discrete functionality, such as reading and clearing a counter, generating a pulse train, and setting a watchdog timeout and a fail state for a digital output. Be sure to visit Opto22.com for more information and to watch our other great screencasts. See you next time.